Hi everybody, in this video we will talk about gases and the theory behind them. As you may know, a gas is a substance that has no definite shape nor volume, and because of that, gases are compressible, such as in this image where the gas over here is compressed down to here, and this goes to show how gases don't have a definite shape nor volume. So because gases are compressible, its volume and shape are susceptible to many factors such as temperature. We will go into that in the future, but let's first talk about what temperature is. Temperature is the measure of the average kinetic or moving energy of particles. And we measure temperature using a thermometer. And two of the most important units we use are Kelvin and Celsius. To convert between the two, simply add 273.15 to the degrees Celsius to get Kelvin, and note that Kelvin does not have a degree symbol like Celsius does. Now let's talk about pressure. Pressure is the amount of force over a certain area, the force indicated by newtons and the area indicated by square meters. You don't actually have to know this for chemistry, but it's nice to know that pressure is just another way of saying force over a certain area. In chemistry, we measure pressure in many different ways. The main way that we measure pressure is by using the standard atmospheric pressure. The standard atmospheric pressure is the pressure felt when an object or a person or anything is 0 meters above sea level. So this could be the sea, and the person is 0 meters above sea level. This person would feel exactly 1 atmosphere's worth of pressure, since there's 1 atmosphere above us. So 1 standard atmospheric pressure measures exactly the pressure felt at sea level. And 760 torr is equal to 1 atm exactly. And another way to say torr is millimeters of mercury. We'll talk about why millimeters of mercury makes sense, since millimeters of mercury might seem like a measure of distance, but it's actually a measure of pressure, as you'll see later. So torr and millimeters of mercury are identical in terms of meaning, and 760 of either of them equal exactly 1 atm. Now another measure of pressure that you might see is a bar. A bar is nearly equal to 1 atm, but it's actually equal to 0.986923 atms. So now that we're done talking about pressure, let's look at what millimeters of mercury really means. So this manometer, I'll write manometer right here, manometer, manometer. This manometer measures the pressure outside. So scientists would put a gas, I guess, on the inside. So they would put a gas right there, and this gas would have a certain pressure. So it would have, in this case, a lower pressure, and on the outside there would be another pressure, which in this case is higher. And the reason why I was able to tell between the two is because if you look at the liquid, it seems like this side is exerting more force than this side, and that's why the overall level over here is higher than here, since you can think of it as this being able to overcome the force of this, and overall you have a little net force that's forcing this liquid up. So that's why this liquid is above this liquid. So let's just say that the outside pressure is exactly 1 atm or 760 millimeters of mercury. What would be the pressure inside? Well, if I told you that this is a tube of mercury and the level here is 3 millimeters higher than here, then we can deduce what the pressure is in there. Since this is higher than this, that means that the pressure outside, so I'll put the outside pressure in blue, minus the pressure on the inside, which is the one in yellow, I guess, is equal to the difference between the heights, which is 3 millimeters. So if the outside had a pressure of 1 atm, or the pressure at sea level, it would be 760 millimeters of mercury, but we won't write the mercury just yet, minus the inside pressure, and that would be equal to 3. So doing math, you figure out that the inside pressure should actually be equal to 757 millimeters of mercury. So notice how the millimeters tell us the difference of the pressure. So 1 millimeter of mercury difference would mean that the outside pressure would be 1 millimeter of mercury more pressure than the inside. So in this case, it seems that the outside pressure is 3 mmHg more in terms of pressure than the inside. So this gas has a lower pressure, and the gas outside that's pushing in has a higher pressure. So that's how you read a manometer, just in case you need to do it someday. But now that we're done with this, let's talk about the KMT, or the Kinetic Molecular Theory, for gases. So this theory states that gases are mostly empty space. This makes sense since gases are these super small particles and they're spread apart, so there's a huge distance between these small particles inside a volume, and that's why gases are mostly empty space. And our second point is that gas molecules are constantly moving and changing in velocity. So this means that all molecules have a different velocity, and they're not all identical in velocity, but the average velocity and the average kinetic energy of the particles are the same for a certain temperature. So in other words, the average speed and the average moving energy of all the particles are the same for a certain temperature, and that is assuming that all the particles are the same gas. Now I have to clarify some things. So at a certain temperature, and remember that temperature means the measure of the average kinetic energy of the particles, at a certain temperature, the average kinetic energy is going to be the same. So no matter what type of particle you are, at a certain temperature, the average kinetic energy of the particles will be the same, because that is the definition of temperature. At a certain T, the average kinetic energy will be a certain number, but the average velocity depends on what type of molecule it is. So if you have a big molecule and it's harder to move, then it will move more slowly for the same average kinetic energy as compared to a smaller molecule, which will move faster given the same average kinetic energy. And I'll show you what I mean, because the formula for kinetic energy is 1/2 mv squared. So at a constant temperature, the average kinetic energy of the particles will be the same. So we can call this a constant, such as a c. And now you're looking at m and v squared. For a certain temperature, we know a k is constant, but that doesn't mean that v will be constant, because v can depend on what m is, because if m is larger, then v will be smaller. So for bigger particles that are harder to move, their velocities, or their average velocities, will be lower. But on the other hand, if you have a very small mass for a gas, like if the particles are super small, like H2, then you will have a higher velocity, or average velocity, for the particles. And this is based on an inverse relationship between m and v, assuming that our k is constant. So just note that at a certain t, the average kinetic energy will be the same. However, depending on the particle, the average velocity may differ between different particles. So let's move on and look at number 3. Collisions are elastic, and elastic just means that the particles of gases will bounce off and not stick to each other. And in addition, attractive or repulsion forces don't exist. So remember, this is a theory, and it's just an assumption we make, and this is not necessarily true, since there are attractions between gases, but for this case, in our KMT, we want to assume things for gases that will make it easier for us to visualize them. And because of that, we assume that attractive forces and repulsion forces don't exist. Last but not least, gas pressure is caused by the collision of gas molecules with the container. So when gas molecules hit the container with a certain force, they will all create a certain pressure on the container. And this is again measured in ATMs, torr, or any other unit that you might want to use. So let's look at equations that give us the kinetic energy for gases. So the first equation to calculate the kinetic energy for gases is, of course, K equals 1/2 mv squared. Now there are two ways you can use this. The first way is if you want to find the average kinetic energy for each particle. Now if you want to find the average kinetic energy for each particle of gas, then you have to multiply 1/2 times the mass of the gas particle times the average velocity of the particles squared. And if you want to calculate the total energy of all the gases in a system, then you simply have to multiply 1/2 times the mass of, instead of a particle, you're going to multiply by the mass of all the particles in total. And last but not least, you multiply by the average velocity of the particles squared. So notice how by changing the mass, we are changing the type of kinetic energy we are finding. So usually you never use these equations because for the most part, we usually tend to not be able to calculate the average velocity of the particles since that takes a lot of equipment. So scientists like to use this formula instead, which gives us an easier way to calculate the kinetic energy per mole of gas. So in order to do this, you multiply 3/2 by R, which is equal to 8.31 times the temperature in Kelvin. So notice how the units for the kinetic energy per mole of gas is written as joules per mole of gas. And note that joules is the unit for energy. So let's do something special. Let's try to find the units for R. So this is unit analysis. So K is joules per mole of gas, and that's equal to 3/2, which is unitless, times the units for R, and the units for T is Kelvin. So in order to isolate the units for R, we simply divide both sides by K, and we get joules per mole times K is equal to R. And notice that putting the moles of gas is actually optional. You could just put moles, because by using this formula, we are assuming that you are calculating the energy for gases, and that's why you don't need to put the gas, because we all know that you're finding the kinetic energy for the gases. So this is the unit for R, and now you have two ways to find the kinetic energy of gases, either per mole of gas, or for all the gas, or maybe for just one particle of gas. And note that if you find the kinetic energy for a mole of gas, then you are able to find the average kinetic energy for a particle of gas, and that's just done by taking your energy in joules per mole of gas times 1 mole over 6.022 times 10 to the 23rd. So it's just converting between moles and particles or atoms or molecules. And I wanted to clarify one more thing. What do I mean by gas pressure? When I say that there is a gas pressure around us at sea level that's equal to 1 atm, what does that actually mean? Well, our atmosphere has a bunch of gas, and the gas surrounds us. So let's just say there's a person here, and the gases actually crash into you, and they exert a pressure on you. And if you're at sea level, at 0 meters above sea level, then the gases will exert a total pressure of 1 atm on you. And the same goes for here. Outside, there are a bunch of gases, and these gases push down on this liquid, with a total pressure of 1 atm. Meanwhile, in here, the gases in here want to push this way, and they exert a pressure of 757 millimeters of mercury. So I just wanted to show you that pressure is not only exerted in a container, it is also exerted all around us, such as if you're standing on the ground, or it's exerted also on liquids inside and outside. And pressure is all around us, and that's all I wanted to say for this video, and have a nice day.